Welcome back, Hackers on Planet Earth 2020. It's right here. This is the final talk of this day, which is day 7 of Hackers on Planet Earth. Can you believe that? 7 days? It's amazing. And it's really an exciting one. We have such a variety of topics here at Hackers on Planet Earth. This is one that's near and dear to our hearts for 2 reasons. Number one is about gaming. It's an intro to game hacking on the NES, the Nintendo Entertainment System. Number 2, it's about hardware, because we're going to feature the Motorola 6502 processor, take a deep dive into that. Our speakers tonight are leethacks and stakfallt. Let's hear what they have to say.
Hello and welcome to the Intro to Game Hacking on the NES. My name is leethacks. I'm a computational scientist, computer science professor, and a computer security enthusiast.
Hello everyone, welcome to Hope 2020. Thank you all for coming out. I'm stakfallt, and I will be giving you the second portion to the Intro to Game Hacking on the NES.
So I'm going to be covering the first section, which is the introduction to the 6502 instruction set, how the Game Genie works, and some tips on write, breakpointing, and editing instructions in the ROM. So here we go, the introduction to the 6502 instruction set. The Nintendo NES utilizes the Motorola 6502 processor, and the 6502 uses 1-byte opcodes. We're going to learn a little bit about those, as well as a 16-bit address space, which is based on memory pages that are 256 bytes each. There are also 56 supported instructions and 6 registers, 3 of which, X, Y, and A registers, are utilized heavily by the application programmers. So I invite you to follow along using the MassWork 6502 instruction reference. You're going to see that pop up a couple times throughout the presentation. So to find that, all you need to do is Google MassWork 6502, and you'll see the instruction set pop up.
Who are you people? What do you want from me?
We want the numbers, Mason. That's all we've ever wanted.
I can't get these fucking numbers out of my head. What they'd learned.
So that's a little callback to Call of Duty Black Ops there. And the numbers that we're referring to here are the actual op codes. So each assembly instruction for the 6502 utilizes an op code or an operation code, and that code is 1 byte in length. You can see here on the table there are some examples, and we're gonna dive into that a little bit more. So on the left-hand side, I mentioned that there are 56 instructions that the 6502 responds to, as well as different addressing modes that can be utilized by some of those operation codes. So there's different addressing modes depending on the operations that you want to do, and some make sense for certain opcodes, some don't. But the basic gist of it is you have different instructions and different addressing modes to affect memory. So looking a little closer at the table here, the table tells you both the opcode and the addressing mode of the instruction. Now granted, you could look this stuff up for each one, but the table gives you a quick reference guide to take a look at the instructions and have a good idea of what sort of addressing mode each one of those instructions utilizes. So just a quick word on the addressing modes. The idea behind an addressing mode is it tells the processor how to interact with memory. So there are different addressing modes, and we're not going to get into the specifics of that. There's a lot of good information out there online. If you want to just Google 6502 addressing modes, you can find out some great stuff about that. Okay, so if you happen to bring up that mass work instruction set that I was talking about, you'll find Appendix A a little ways down the page shows the details for each of the instructions, including how many bytes total that instruction is and what the opcode is. So if you consider the way that the ROM is laid out in memory, right, each instruction is 1 byte in length and then may have follow-on bytes that indicate what happens with that given instruction. So in the case here where we look at the ADC instruction, add memory to the accumulator with a carry, we can see here that there are different addressing modes for the ADC instruction. Some of those include the immediate addressing mode, the 0-page addressing mode, and then absolute and indirect addressing modes. So with immediate, what happens is you specify the 1 byte opcode, so you would see 69 in memory, and then you can see that this is a 2 byte instruction. So the first byte is the opcode, and then the second byte would actually be the number that you want to add to the accumulator. So for example, if you had the number 10 in hex, you would have 6910 laid out in memory, and that 10 would be added to whatever is already stored in the accumulator A. Similarly, if you have a 0-page instruction, 65, this is also 2 bytes in length, and the follow-on byte there tells you where in memory on the 0 page you can find the value to add to the accumulator. So using my example again, if we had 6510, what we would do is we would go to memory address 10 and find whatever value is stored there and then add that to the accumulator A. So those are a couple examples, but the idea is each opcode is 1 byte, and then there may be trailing bytes that also sort of either have an immediate value or refer to a value that's in memory. So here's another instruction. This is the NOP instruction. And the NOP instruction is used to tell the CPU not to execute anything during those cycles. This becomes an important instruction for game hacking, if you will, because a lot of times you want to override the functionality of certain commands and effectively patch them out. So one easy way to do that is to patch in NOPs over existing commands. So let's talk a little bit about the Game Genie. With the Game Genie, the device temporarily modifies the game data, allowing the player to cheat, manipulate various aspects of a game, and sometimes access unused assets or functions. So let's look at how this thing works. So it's an intermediate device, and it's shoved between the game cartridge and the game console. So effectively, you have the cartridge plugged into the intermediate device and then the intermediate device plugged into the console. What happens is the intermediate device can intercept certain instructions from the cartridge and effectively overwrite those instructions with customized instructions. So there's a little flowchart here on the screen, and we're not going to get too heavy into the details. But the basic gist of it is, if the console is requesting memory that exists on the cartridge, and that cartridge memory location has been specified in the Game Genie for replacement, the Game Genie will replace that opcode and trailing bytes with whatever has been specified in the Game Genie codes. Right? So we're going to talk a little bit about that. But the idea is, when enabled, the intermediate device can block the game cartridge from returning certain instructions and instead return patched instructions. Okay, so let's take a look at some instructions here. You can see that we have some instructions here. We can see increment 1200, LDA 1200. This is load into the accumulator. Compare against 3, find out if this is the third lap, branch if not equal to, and this is telling you where to branch to. Otherwise, it'll jump to the race has been completed. So the idea here is you may want to patch out this BNE and jump directly to where the race has been completed. The way this lays out in memory, this is going to occur sequentially. So you'll increment 1200, LDA 1200, compare 3, and then you could potentially patch in 2 NOPs here because you have 2006, 2007, and then you would go to 2008. So if you were to patch in 2 NOPs here, what would happen is you would immediately finish the race regardless of what the comparison returned. Okay, so that's one of the things that we're going to look at today, is how to patch out certain functionality in the game. Another thing we're going to look at is the specifics with the Game Genie codes. I figured this might be worthwhile to take a look at, right? So the idea here is a Game Genie code is essentially a word, right? And it's a word that consists of characters, but those characters map back to hexadecimal values, okay? So the table on the left-hand side over here shows you what the characters correspond to in terms of their hexadecimal values. So for example, an A is represented by hex value 0. A P is represented by hex value 1, and so on and so forth until you get to the N, represented by hex value F. Okay, so for the code gossip, right, that code gossip is actually encoding both a 15-bit address as well as an 8-bit data byte. Okay, so what happens here is this code both encapsulates the location of the patch as well as the value to be patched out. And there's an equation that we're going to look at to figure out what part of this corresponds to the address, what part of this corresponds to the actual data component. So first things first, let's break this string gossip into its components. So we're going to look at N0 through N5 and map each one of these characters to their hexadecimal equivalents. Okay, so the G, if we look at the table here, represents hex value 4, the O value 9, the S value D, the I value 5, and the P value 1. Okay, great. So now that we know that, we can actually look at the equation to figure out what address this corresponds to. So what happens here is the address is equal to hex 8000 plus this, this expression here. So let me just walk you through this. If you've never seen Boolean algebra or bit shifts or anything, this might look confusing, but it's actually quite simple. So in this case here, we're going to evaluate this expression from in to out, just like you would in any mathematical expression. So what we're going to do here is we're going to take the value of N3 and that with the number 7. So N3 and 7. You can do this on a calculator, obviously. You don't have to do it by hand. So N3 and 7, and then these two less than signs are the left bit shift operator. So N3 and 7 produces a result, and then we left shift that 12. Okay, so that result would be 101, and it gets left shift 12. This green 1 over here corresponds to the 8000 in hex, right? So we're just going to build this expression piece by piece here. Okay, and because all of these are ORed, you can see these pipes here represent the OR character. We're just going to add these bit strings together and let the ones fall through. Okay, so N3 and 7 left shift 12, or N5 and 7 left shift 8, or N4 and 8, left shift 8, right? And we go down the table here and we fill these in as we've solved them, and we add them all up. So in the end here, you can see there's no left shifts on these last two in the expression, and you wind up with 101 and then 1000 respectively. Anyways, you add them all up and you get this extremely long bit string here, and all of that boils down, if you were to dump this into a calculator in binary and convert it to hex, you would get hex address D1DD. Okay, so this is where on the cartridge, the address on the cartridge that you would like to perform your patch. Okay, so that's the 15-bit address plus the 8000 gives you a 16-bit address where this one is always constant. Okay, so we talked about where on the cartridge we're gonna create our patch. Now what we need to do is actually figure out what value is going to now be patched in there. So in the case of gossip here, that data byte is found by doing N1 and 7, left shift 4, or N0 and 8, left shift 4, or N0 and 7, or N5 and 8, right? So we figure all that out, we add them all up, and we find that it comes out to hex value 14. So what's going to happen now is whenever the CPU reads from address D1DD, the Game Genie will intercept that read request and return the byte 14, hex 14, in place of whatever byte was stored in that location on the cartridge. So imagine that byte used to be FF. Well, now when a read request comes in, it's going to be 14. Okay, so you can do this to patch data bytes, or you can do this to patch instructions. Really, the NES doesn't care either way. Okay. So now that we've seen that, what we're going to do is take a look at how you would go about creating your own Game Genie code. And this is really the inroads into hacking your own NES games, right? So I really break this down into two phases. The first phase uses Bizhawk, it's an emulator, and the second phase uses FCEUX, it's also an emulator. It's up to you which tools you want to use. There's a bunch of good tools out there. You don't necessarily have to do it like this, it's just one way of doing it, right? So in phase one here, what we're going to do is identify a game, launch the game with Bizhawk, identify an interesting characteristic, identify a memory location where that interesting characteristic is stored, and then we're going to freeze and poke memory to determine if we have found the desired effect in memory there. So phase two, once we've verified the address that we're interested in, we can then add a write breakpoint for that memory address, and we can use that breakpoint to determine an address of interest on the game cart itself, okay? So we'll use the debugger to inspect that instruction and determine its opcode and corresponding data bytes, and then we can use the cheat window to patch the codes with NOP instructions. You can obviously patch with anything you want, but the NOP instruction works pretty well in a lot of cases. And then finally, you're just going to activate your cheat, check the debugger to ensure that the proper instructions have been replaced and that no undefined behavior exists immediately following your patch. And once satisfied, you're just going to record your cheat codes for use later. So this is going to allow you to create your own Game Genie codes, which is kind of cool. So, okay, how do we do this? So the first thing you want to do is launch a game, right? And identify an interesting characteristic, right? So what is it that you care to hack, right? How many lives you have left, how many moves you have left, your current power level, the amount of time you have left. There's a bunch of different things that you could potentially hack. So we're just looking here at the status bar in a game, and you can see these different attributes are represented here. The total score, how many lives you have left, your speed, and your weapon, right? So let's say, for example, we wanted to hack how many lives we have left so that we essentially have infinite lives, right? So this is in the Bizhawk emulator, and I'm just using the memory search feature in that emulator, right? So we identify a memory location where an interesting characteristic is stored. So to do that, we play the game, right? And when we lose a life in the game, we can see that this interface here on the status is updated, but correspondingly, the memory is also updated, right? So what we're doing here is we're looking at change counts, and we're seeing that, okay, in the time since we died, this value in memory has only changed one time, and it used to be, its previous value used to be 3, and now it's 2. Now in this particular game, this is really easy. They did us a solid here by keeping, 3, 3 and 2, 2, and it's, exactly what you see on the interface is what you see in memory. That's not always going to be the case, right? Some games are much more tricky about how they lay things out than others. But in this case, we've identified memory address 0034, and we can see that, in the time since we died, the value has gone from 3 to 2. So we're going to just kind of stick a pin in that and say, okay, this is probably an area of interest. We may also identify other addresses that have similar sort of look and feel to it, and we may also want to potentially identify those and keep those on the back burner. So what we want to do here now is we want to freeze this area in memory, right? So what we're going to do is freeze and or poke memory to determine if that has the desired effect. So in this example here, I can freeze memory address 34 and I can keep that value constant at 3. So in other words, I can take a death in the game, and because memory address 34 is frozen, what happens is that value stays at 3, right? So no changes to that value occur while that memory address is frozen, okay? So that now means that the behavior has been verified in the game. So once we've verified that address, we can now move on to the second component, right? So it's important to understand that the NES itself has RAM, right, memory, and these values as you play the game are stored in RAM. So that's great. However, the Game Genie can't access the RAM on the console, right? What it can do is it can intercept instructions on the game cartridge, and it can replace those instructions, right? So we're not quite there yet, right? We've identified where in RAM the value that we're interested in is, but we haven't actually patched this on the game cart yet. So that's going to be phase 2. So we now know where in RAM the value of interest is. So what we're going to do is move into phase 2. Once an address and relevant data values have been determined, we can now move on to the write breakpointing aspect. Okay, so in this case here, the address from phase 1 is 0034. We're going to launch the game with FCEUX, open the debugger up, and we're going to add a write breakpoint for the memory address. So that's as simple as just clicking the little add button there, and then you type in 0034 and you check off the box for write breakpointing. What this means is that the debugger is going to pause whenever memory address 34 is being written to. So what this is going to allow us to do is find out when the cartridge has an instruction that writes to that memory address. Okay? So in this situation here, we're going to use the debugger to inspect the instruction and determine its opcode and relevant data bytes. So we run the application, activate the breakpoint, and take a death, right? So when we take a death, this address, C345 on the game cartridge, is jumped to, and we can see that it has an opcode of D6 and a corresponding data byte of 34. So if we take a look at Appendix A from that instruction set, right, we can see that DEC is decrement memory by 1, which makes sense. If you take a death, you're going to lose 1 life. And we can also see here that this is a 0-page instruction, meaning that we are going to go to memory address 34 and decrement that value. And that's actually what we sort of saw happening in RAM before when we were looking at this through Bizhawk. So now what we've done is we've identified where on the cartridge the instruction is that decrements that address. Okay? So the next step here is to perform a patch, and what we're going to do is we're going to patch with NOPS that behavior. So we're going to go to address C345, and we're going to patch opcode D6 with EA, right? EA is the opcode for the NOP. So what we're going to do is we're going to go to C345, we're going to look for D6, and we're going to patch that out with EA, okay? But because NOP is 1 byte, okay, and the decrement operation was actually 2 bytes, we need to be extra careful about that and also patch out byte C346. Now, C346 isn't shown here because that is the 34 that corresponds with the memory address that we were interested in. So what we're going to do is go to C346, find value 34, and now patch that out with EA. So what happens here is we wind up patching out these 2 bytes in memory with these NOP instructions. Once we do that, we can now get our Game Genie codes and activate them, and your patch will temporarily replace the code read from the game cartridge. So in this case, we've scored infinite lives, and we did it ourselves. So that's really awesome. Okay, so that concludes my portion of the presentation. You're now going to be joined by stakfallt, who's going to do a deep dive on the picture processing unit. I hope you enjoyed, and have a great night.
So the first thing that you're going to notice about the PPU's memory layout, or the picture processing unit's memory layout, is that the addressing space is very heavily organized in where certain data is loaded and how the data is used. There's also some strange to very strange things about the PPU that we'll be going a little bit more into detail about. Certain parts of the memory are mirrored. The PPU memory layout is broken up into 4 tables. Essentially, there are 3, but you'll see why I say 4 in just a second. So it's the pattern table, it would be the name table, and this is where the 3 or 4 tables kind of come in. So the name table is made up of the tile map and the attribute table. And then the 4th one would be the palettes. But time permitted, we may not be able to get into palette. The general layout of the memory starts with the pattern tables first. There's the background pattern table, and then there's the sprite pattern table. And then there's the name table. And the name table, as I mentioned before, is composed of the tile map and the attribute table. Then there's potentially up to 3 more name tables, depending on the NES card that you're looking at. Typically there's 2, but some NES cards can support up to 4, 0 through 3. And then, of course, the palettes. The pattern tables are probably one of the more complex aspects of the PPU memory. And it contains not just the shape of the tile in pixels, but also the color. Now, there's a little bit of terminology that we have to kind of go over in order to really explain this. So if you look at what a tile is nothing more than a square of 8 pixels across by 8 pixels down. Now, you basically paint with those tiles to create your background and your sprites. And every byte is an entire row. Now, obviously, it's 1 bit per pixel, and whether it's a 1 or a 0 is on or off. Now, each tile has 16 bytes. So to the astute observer, you may be thinking to yourself, well, how can there be 16 bytes if each byte is an entire row and it's 8 by 8? Well, you're going to see that there's actually sort of like partner bytes that are concatenated together. The bit columns, more specifically, are concatenated together. And the color index is based on that concatenation. And we'll go into much more in-depth on that. The name table is made up of tile indices. Now, that would be the tile map. So the tile indices are numbers that refer to the tile that is in that particular pattern table. And then there's also the attribute table. So when you look at the tile map, it's considerably easier to deal with than the pattern table. And each byte refers to an index, to the tile index that is referenced or created in the pattern table. So the name table up to 4 can be supported, 0 through 3, as I mentioned before, and each byte is a tile index. The tile map is 960 bytes long, And the attribute table is 64 bytes long, giving you 1024 bytes or 1 kilobyte. So typically you're looking at cards that have 2 kilobytes of RAM. So the attribute tables contain the pattern number. Now, if the pattern table provides the color index into the palette number, into the actual palette number itself is assigned by the attribute table. And it is always at the end of the name table. And like the tile map, there's 1 byte per entry, and the screen is broken up into 4x4 tiles. I'll actually show you the bytes and how it's all broken down in just a little bit. But just know that each 2-bit tuple refers to a quadrant of tiles. And a byte of, say, for example, E4 refers to it goes from left to right, top to bottom, I believe. It might be the other way around. I always get them backwards. But so let's talk a little bit more about the attribute table. So the background sprite attributes are handled differently. And so the background sprites they're a little bit more of a pain to deal with than regular sprites. The attribute assignment byte is broken up into 2-bit chunks, and a chunk is a tile set of the block. And later, when I show you the diagram that I've done, you'll see exactly what I mean by a tile set versus a tile versus a block and all that. Just recognize that palettes are assigned to basically a block, which is 2x2 tile sets, which is 4x4 tiles. So if you'll notice, I actually have the CPU memory map in tandem with the Ppu memory layout next to each other. And the reason why I did that is because when you look at the memory locations in something like Messen, which is like one of my favorite emulators, it's easy to get a little confused because you'll see address 0000 in both CPU and Ppu memory layout, and you'll be thinking to yourself, well, are they the same? And the answer is no, they're not. In fact, the Ppu is on a completely different address bus than it's not read or write to the Ppu memory directly. So, and the CPU memory, when you look at that's just a sample on the side there. It's just a sample of like what could be the memory layout. It's all going to depend on how the NES game was coded. Now the Ppu memory layout, you'll see that is actually pretty heavily organized in terms of what goes where. And this is just a visual aspect. You'll see, there's like the tile map and then the attribute table, and then there's the palettes. But let's actually break down the data where the rubber meets the road and actually show you how the bytes are broken down. And looking over here, we can see a sample of a name table. And over here where there's an arrow, you can see the 4D, 0x4D in hex. Now, how that breaks down is pretty interesting in the pattern table, but we'll talk about that in literally just like a second or two. But you'll see, if you load up Messen and you load into the name table viewer and you click on a tile, you can see that it gives you all the information about the tile. You can see that it's tile index 4D, just like 4D over here in the bytes. But you'll also see the tile address, the 14D0. Now, that's significant because when you look over at the CHR viewer, as well as the pattern table, you'll see how that particular tile is made up from the bits. So each row is a single byte, and a tile is 8 pixels across by 8 pixels down. And so you might be saying, okay, well, if a single byte is an entire row, then why is there 16 bytes? That's where it actually gets a little strange. So the colors on each of the bytes I put there to show that there's a corresponding partner byte. So if you look at this 0A here, there's a corresponding 0A, a stride length, let's say, like 8 bytes beyond, because it's 16 bytes and you divide it in half. Now the 0A breaks down so you can look at the halves as left and right or A and B. It doesn't really matter. I choose A and B because if you look at the number of columns, I have it set to 16, but if you have it set to something like 8, it might not be left and right at that point. So I go with A and B. So we'll look at left side as being A, right side as being B. And now when you look at how that's broken down, you see byte A over here and you see byte B, and then it's the binary values underneath that. Now, where it gets interesting is when you look at how these values are concatenated. It takes the byte or the bit in that column of byte A and concatenates it with the bit from the corresponding column in the corresponding byte B. So if you look at 0A and 0A, you know, bit 7 of A is 0 and bit B, or bit 7 in byte B is 0. Put them together, you get 0, 0, so, which is summation of 0. So that means the 0th color in that palette that will be in that block of where that tile will be painted on the background. And the same thing for the first bit, or I should say really the second bit. You can look at a sub A and sub B, 1, 1, concat them together, and you get 3. And you get 3 because the first bit column is 1, and then the second bit column is 2, and you add them together because they're both on, you get 3. So that means the third color in that palette. And that's why you have 2 sets, because it concats the bits together to create not just the color, but when you look at whether the pixel is on or off, it also gives it the shape, whether it's on or whether the pixel is, whether there's a pixel there or not. So if you want to look at, say, the tiles and how a screen, the background is broken up in the NES, like this. So you all know that a tile is 8 pixels by 8 pixels. Well, if you look at a tile set as 2 by 2 tiles, that's 16 pixels across by 16 pixels down. A block would be 4 tiles across and 4 tiles down, 4 by 4. And that is the smallest space on the screen that a palette can be assigned to for a background on the NES. Now, sprites are different. Sprites are a single palette, but it's stored, the color for the palette is actually, the color index that's into the palette is actually stored as part of the sprite data. So it's a lot easier dealing with sprites than backgrounds. But this is how a background is actually drawn together. It's drawn up with tiles that are in the tile maps based on the index of it in the pattern table. And then the pattern table gives it not just the shape, but the color. So that should actually help explain a bit. And when you look at the blocks and the attributes, I think I actually have a sample. Yeah, so if you look here, you can see 2C00. Now 2C00 starts the name table 3, but just before that will be the attribute table for name table 2. So this would be like what the name table 2 data would look like, and it's basically 5 a bunch of times and then FF and so forth and so on. And they refer to the palette, the actual palette number that's stored in the palette table down at the bottom of memory layout. And that's where you get like 0F, and that 0F corresponds to here as a 0th color, and 2 corresponds to this color, so forth and so on. And so you can see how if this is color 0, color 1, color 2, color 3, well, that's what these are over here from the pattern table. So as you can see here on the name table sample, these bytes of 55 and FF, and how they actually dictate the palette is, as I said before, the screen is broken up into blocks. And if one of these is a single tile, and there's 2 by 2 for a tile set, and then you have 4 by 4 for a block, the way that works is if you look at this 4D right here, that 4D correlates over here to being broken up into this binary value. So the way the binary values are applied to the coordinates is, again, it's in 2-bit tuples. So this first one gets broken down into 0 and 1. And then the next one is 0, 0, 3, and then 1. And that is what the palette number is for that tile. And then the pattern table tells you what color is inside that you're going to be using for that particular quadrant in that block. So let's go back over to this, and you'll see, so like that 0F, 22, these are the palettes. So they're in 4-byte increments because each palette is 4 colors. And it's 0, 1, 2, 3 for the palette. and then it just kind of repeats, and it's copied and mirrored. But so when you look at the attribute table, these are the palette numbers that it's referring to. This block, this set, or this set, or this set, or this set. And then the pattern table tells what color in that set. So if we look over at Messin real quick, and we bring up the PPU viewer for one of my favorite games, Metroid, you can look at the name table viewer. So if you wanted to get, say, let's see, let's pick a spot somewhere. Let's go with this one right here. This section, this top corner right there. And if you turn on CHR viewer, but you turn on, I think it's going to be that one. And then you go into name table viewer. You can do highlight tile selected in CHR, and you can see what tile you selected. So we were looking for that corner piece right there, which would be, we don't want that. We want this one. So this is going to be tile index 01. So it's going to be likely that. No, let's try that again. 01. This one. And yeah, it is. Okay. So this is the palette that's being used, and then the pattern table tells you what color. So as I mentioned about the breakdown of the screen, if you want to look at it, like if you want to get a better visual, you can turn on the tile grid. Now, as I mentioned, each one is 8 pixels by 8 pixels. You can see how each tile is in here. But then if you turn on the attribute grid, you'll see actually where the palettes are assigned to in those quadrants. So if you look at, let's see if I can find one here, 23cc. Okay, so it looks like we're on the edge of one, yeah. So if you look at where the mouse cursor is next to the selected tile, you'll see that the attribute address right over there is 23cc. Now, if you follow the cursor over, you'll see that it continues to be 23cc until you have reached 4 tiles over, or 2 tile sets. And it's also 23cc, 2 down, because, or 2 tile sets, and then 4 down, or 2 tile sets. So then if you look and you go down, you'll see that the attribute address changes. Now the way that works is, as I mentioned in the spreadsheet here that I did, you can see that these are the palettes that are assigned to those quadrants. And as the bytes change and they get filtered down to the bits, you can see the palette assignments for each of those quadrants. And that's basically how the colors of the PPU and the sprites are worked. So you should be able to, with that knowledge, do some sprite swaps and color swaps and play around with the graphics a bit. So I think that concludes my portion of the Intro to NES game hacking. Thank you all for coming, and we'll be available for questions.
This is fascinating stuff. As I said at the opening, this is what Hope is made for, right? This is arcane knowledge. You spend hours and hours digging deeper and deeper, trying to understand what's going on, and that's what a lot of us do. And the Hope concept is you show up here and you share it. So thanks very much to leethacks and stakfallt for sharing this. I think I want to just give me a little bit of the basic background. Maybe you could tell me a little bit more about your software, and if there's a link to the software that you can share with the hacker community.
Yeah, so in my efforts to understand the PPU memory layout and how it all works on a hardware level, as well as programming for that hardware, I wrote a NES ROM from scratch using NES ASM, which is a free available tool. It's written in assembly. I use RAD assembler for my IDE. None of it is actually up on the GitHub yet, but I will be publishing it to my GitHub. I will be publishing a project file for RAD assembler, so you have the ability to create NES ASM project files for it. I will also be publishing a lot of the game hack addresses that I found, just trying to mess around a bit with Castlevania and stuff like that. As well as, I think I might even put up my Visio slide, so you'll have the full diagram of that. There might be some other things in there too, like some Lua scripts that I wrote for the emulators and stuff. But yeah.
Yeah, wow, something to look forward to. I don't know if you mentioned, or maybe I missed it in your presentation. Did you give your GitHub?
No, that's just github.com/stakfallt.
Stakfallt. Okay, so basically the same as your username. Someone had asked in the chat whether this applies to the new mini NES, or is that actually a totally different beast?
So that's gonna, as far as I know, the NES Mini, the classic, is based on it's using an ARM processor, and it's running on Linux. So as far as whether it would probably apply to the emulation system that's running on the processor, but not to the processor itself. Because when you think about it, you're dealing with like a Ricoh developed MOS to Ricoh, to Motorola. You're dealing with a different type of processor than the ARM.
Yeah, multi-step.
Yeah.
So somewhat relevant. I guess someone else had asked, maybe a little more recently, we've had these Nintendo source code leaks, and has that interested you? Did you learn anything from it?
I actually hadn't heard about that. That sounds kind of fascinating, though. Lee, have you heard about that?
Yeah, of course, man. Luigi is real in Mario 64, apparently. So,
Nice.
yeah, I heard about it. I think it is fascinating. I've been watching a lot of the YouTube videos about it and stuff like that. One of the things I will say regarding the little presentation about the Game Genie and all that kind of stuff, I was talking about using Bizhawk to sort of identify memory addresses and how you can hold a memory address constant. And a lot of the modern day emulators, if you're doing this stuff in emulation, you can kind of stop there. You don't need to go the route of write-breakpointing and doing all the additional steps that I was doing. But the cool part is if you do actually take it to phase 2, that'll work on any of the original hardware. If you happen to have a real Nintendo system and a Game Genie lying around, you can actually implement those hacks on the original hardware. So that's the cool part about that is like, yeah, you can stop at phase 1 with modern emulation technology and be good to go, and that's super easy to do. But you can actually go full bore into phase 2 and then do that on real hardware, which is the cool part.
Is it fair to say that you've looked across the whole entire library of eligible NES games? Did you really do a pretty exhaustive, set?
Definitely not. No, there's too many of them.
So you just chose some of them, because someone was asking in the chat, they were wondering what was sort of the most impressive from sort of a, maybe it's a code efficiency, memory use, all these tricks that you have to do to really get the most out of this relatively small system.
So one of the things that I noticed, I was trying to break apart the randomization routines in Who Framed Roger Rabbit. And I will just say that that game, in my personal opinion, I'm sure there's people that disagree, but in my opinion, that game is a mess. I mean, when you look at how much memory is trampled and just rewritten and read and rewritten, it's like it's all over the place. So just trying to figure out and break down how the randomization works in that game is just horrendous. That said, the interesting thing I did find about things like Castlevania, which I would say that a lot of game studios probably develop many of their games a similar way. And if you take something like Castlevania or Life Force or Gradius, they all have the same similar style status bar. And when you look at the status bar, one of the interesting things that I found was it's basically painted as a background. But the way they wrote it was they did offsets into where the areas are to update for the background. So they could create basically fields to update based on just the offset of that they were specifying for that label.
So it sounds, when you started talking about Roger Rabbit, what it sounds like was that was a counterexample. So maybe not a great way of doing things. That got me thinking of another question. I mean, your bio mentions being a computer science professor, and I was wondering whether you teach things related to game hacking, or if game hacking you think is a good topic for computer science students to learn.
Yeah, so absolutely. I teach an upper level CS course in computer organization, and we introduce assembly in that course. And the way that I do that is by teaching basically this lecture as well as some others as well. So I think it's super valuable because the kids get interested in it, right? I mean, that's the whole idea is that you can kind of bind this to something that they're naturally interested in. And from there, you see a lot of results. The kids get interested in it. They have something tangible to work with, and they can see their results. So, there's a point to them learning assembly language.
Wow. I think I speak for all computer science students who wish that they were learning game hacking alongside assembly language rather than just assembly language. So do you want to, we're just at the end of our time here. Did you want to share a screenshot of some of your software that might be worth just spending our last half minute or minute on?
Yeah, sure. Give me just a second. Just make sure we okay. All right. So over here, you guys can see it, right?
Yep.
Yep. Okay. So over here, you'll see the RAD assembler that I'm using, the IDE. And I broke it down into different libraries and stuff. But over here, you'll see the different emulators that I have running. I have Messen, I have Bizhawk running. Now, when I was trying to debug the palette loading for the NES ROM that I wrote, I had to write some scripts in Bizhawk just to kind of make sure that my palettes were loading where they were. And one of the things that I was finding was that a lot of the emulators, despite being called emulators, don't actually seem to emulate the hardware the way they're supposed to. So if you look at like here, this is the palette data. Now you can see the bytes here, but if you switched over to say something like NESHawk and you do reboot core, that's actually the CPU memory there. But either way you look at it, these two right here are literally the same ROM. But over in Bizhawk, it's not actually shifting to palettes, yet over here it is. And the way I did the palettes was just to kind of simulate sort of like a sunset. And there's only so many colors you can choose from, and so many colors in the palette. So it was like I did the best I could. But you can see like I have the input system working. It moves around. You can see the up down arrows, the sprites showing that those are the keys that you're hitting. You hold up down code and all that, and BA select start and all that. And I'll be putting this up on the GitHub, so people will be able to look at it and play around with it and make some modifications.
Fantastic.
Yeah, I would go through the library, but there's just not enough time.
Yeah, we're actually out of time.
All kinds of stuff for it.
Probably the thing to do is just end with the GitHub link again, so that people can follow up and possibly through GitHub. It sounds like they should be able to get in touch as well if they have.
Yeah, it would just be github.com/stakfallt. Sierra Tango Alpha Kilo Foxtrot Alpha Lima Lima Tango.
Thank you so much for bringing us this exciting demo. I think we had a lot of good engagement in the Matrix chat as well. People are wondering a lot of things about what you can learn from this code and what you can discover, about especially about how essentially small memory footprint coding can be relevant in the modern world where we have far greater resources. So I think that discussion can continue. Thanks again. This has been leethacks and stakfallt telling us all about hacking the NES.
Thanks, Craig.
Thank you, gentlemen.
Thanks,
we are done. This is the end of Hackers on Planet Earth Day 7. We've surpassed all the records at this point, right? We're just cruising towards Day 9. Join us tomorrow. We got a lot more excitement upcoming, and tonight, for those of you that are watching this live, in about 7 or 8 minutes, we're going to have a fantastic DJ set and visuals. So every reason to stay up late here at Hackers on Planet Earth 2020. Thank you, gentlemen, and good night.